Okay, so this video is going to be pretty brief. It's just that visual representation of some of the words that we were using earlier in order to describe different pathways. So a pathway is going to be either catabolic or anabolic. It's going to be breaking something down into smaller pieces, or it's going to be taking those smaller pieces and building back up to something big. You do have amphibolic pathways, which do a little bit of both. You'll only learn one, maybe two of those throughout the quarter. But mostly, you can go ahead and make yourself a piece of paper, left side, right side, catabolic, anabolic pathways, and just start keeping track of what's doing what. Basically, this is saying that this side is how we're going to get some quick energy out of our food. But it's also saying that if we haven't had food in a while and the body needs to start getting those energy stores from something else, that's when you break down your glycogen that's stored in your liver or your skeletal muscle. It's a catabolic reaction. It's breaking those things down so that we continue to have energy for the body, the red blood cells, the nervous system, etc. So that's also going to lead into, if your body has used its glycogen and still doesn't have a meal or food to go by, then the next step is that it's going to break into your amino acid stores in your skeletal muscle. And then your body knows it can't do that for very long. It's not sustainable, so that's when you break down into your fat stores. And I'm going to kind of talk a little bit about the order of those things with the next video. So, but the flip side of that is that if you eat and you are fully fed, your body has the initial immediate energy taken care of, then that's when your body does anabolic reactions of replenishing your glycogen, replenishing your skeletal muscle, replenishing your fat cells, having enough fuel to make your hormones, all that good stuff. So catabolic, anabolic, that's your first layer to this. And remember, I was saying in the first one about layers, if you kind of clump some of these words together, you don't have to memorize so many different separate things when it's the same idea of what they mean. So this is layer number one. The second layer is going to be oxidative versus a reduction reaction. So the left side, if it's catabolic, it's also your oxidation reaction. So this is your oxidizing side. This is going to be your reduction side. Your third layer is going to be just describing the energy that's being yielded or used. So on this side, energy is being yielded, so it's considered an exergonic reaction with a negative delta G. So you've got exergonic with your negative delta G. And then on this side, energy is being used. You're actually needing energy to build from something small back up to something big. And that's going to be your endergonic, or your positive delta G. So those are your 3.5 or 4 layers here. Pretty much telling you the same kind of idea. Something's getting broken down, it's oxidized, it's catabolic, negative delta G. Just start putting those words together to go ahead and have an idea of what's happening here. Last little point I want to make about this is just tying in to this schematic, the whole transfer energy stuff. This isn't going to be a perfectly accurate depiction of this, but the idea is there, so just bear with me on it. As we break things down here, as we oxidize them, we're releasing those hydrogens. But we can't just release a bunch of free hydrogens into the cell, because what are a ton of free hydrogens floating around? It's acidification. So your body, in your cells and in your blood, you have a very narrow range, you have a very narrow pH range that you can exist with. And so you can't have a bunch of these hydrogens floating everywhere all the time. So that's why when we pull a hydrogen off of something that we're oxidizing, we're not just pulling it off and letting it float around, we're pulling it off and we have to give it to something immediately. And that's going to be your transfer molecules, the NADH or the FADH2. So when we pluck off these hydrogens, we then give those hydrogens to the NADP, or I'm sorry, not NADP. We give those hydrogens to NAD+. You get the picture. And what we have then is NADH. And so now we've oxidized what we're breaking down, and we have now reduced our transfer molecule. Always have in mind what this terminology is with oxidation reduction. So now that our transfer molecule is reduced, it's now able to give its hydrogen to something else because it's a transfer molecule. It's transient. It doesn't exist like that for very long. It's constantly turning over. So what it can do now is it gives that hydrogen back available for the reduction side. So again, this isn't exactly how metabolism flows, but I think that this helps kind of understand how these two arms connect, if that makes sense. If the body's in a catabolic state, it's not in an anabolic state. So this exactly is not what's happening. But if this helps you to understand the fact that we pluck them off of here, give them to the transfer molecules then deliver them somewhere else, or have them available to then do the endergonic reactions, great, purpose served. So yeah, hopefully that kind of helps get a visual schematic of what's going on with clumping these words together. Keep it simple.